Good morning, Gainesville. My name is Sarah, and I'll be your host today talking about a phenomena taking the chemical engineering community by storm. Drag. What is it? Drag comes in two types. Skin drag, when fluid flowing past a body within a thin boundary layer around the surface is subjected to shear stress, and form drag, which is an additional stress from the directional change required to move around the body outside of the boundary layer. First, the fluid is brought to a screeching halt at the stagnation point at the front and center of the body. It flows around the body until it reaches a separation point where the streamlined parts. The location of this point could be as close as the center of a sphere or as far back as the end tip of a streamlined body, depending on the morphology and the Reynolds number of the fluid. There's only so much stress a fluid can take. Just how much is enough for these immersed bodies? The total drag force depends on the geometry of the body and the flow characteristics in the following way, which is very similar to the way drag force is defined for internal flows like porous media or flow through tubes. There is a dimensionless drag coefficient, a projected area perpendicular to the flow, density, and stream velocity involved in this variable. It's a complicated, some might even say turbulent, relationship between drag coefficient, shape, orientation of the body in the fluid, and Reynolds number, but there are a few common simplifications. In a laminar boundary region around a sphere, the drag coefficient is about 24 divided by the Reynolds number. For systems with Reynolds numbers between 1,000 and 20,000 or above 50,000, the drag coefficient is constant for a given geometry. Now, if the suffering of the fluid or the convoluted relationships with geometry and flow haven't convinced you, we have a few more reasons to put drag on your watch list this season. Chemical engineers across the world are afflicted by frictional losses due to drag around immersed bodies, but some have found ways to use it to their advantage. Let's take a look. First, water treatment involves clarifying steps, which separate particles by their interaction with the fluid.
2. The settling zone provides the calm area necessary for the suspended material to settle.
That video is from the American Waterworks Association. Another important application of shear stresses in fluids are also important to tissue engineers, as fluid flow past cells influences their growth, orientation, and release of cellular products. These engineers attempt to control the shear stress by maintaining laminar flow instead of turbulent, or manipulating the geometry of the reactor to get a further grip on shear stress. Here's an example. Finally, spray drying depends on drag and flow and has applications in everything from food to pharmaceuticals. Awesome. Now let's look at an example. We're going to find the force on a sphere and the drag coefficient. We have air flowing at 37.8 degrees Celsius and 101.3 kilopascals and a free stream velocity of 23 meters per second. Our first step is to gather the important information like density and viscosity of the fluid. Second, we'll calculate the Reynolds number. This leads us to a C, or a drag coefficient, of 0.47. Then we'll find the force. Here's an example of what the projected area might look like. For a sphere, it becomes a circle with the maximum diameter. Plugging this into the force equation, we have force is 0.1958 newtons. Put this into perspective. One keystroke on an older laptop takes about 12.9 newtons. But if this were thousands or millions of spheres, things would add up. One more example. Calculating the force on a submerged cylinder. We'll be looking at flow past a cylinder in a large tunnel, and the fluid is flowing perpendicular to the sphere. Our goal is to find the force per unit length on the cylinder. Again, we'll gather the important information first, density and viscosity of the fluid. Second, we'll find the Reynolds number, and then the drag coefficient. Here's what the projected area would look like when the fluid is flowing past the cylinder in a perpendicular to the axis of the cylinder. It looks like a rectangle with the same height as the diameter of the sphere. Once again, we can plug into the force equation, and this amount of force is a bit larger. That's like 5 keyboard strokes. And with more exposed surface area and more fluid density than air, it takes a lot more force. Not a coincidence. Thank you. Back to you, Jan. That's like 5 keyboard strokes. And
honey. It's so hard being a fluidized bed. Nobody really knows what we even do.
I know, but it's okay. You got this. You must inform everyone. They must know.
No!
Hello, scientific folk, old professors that are about to croak, and those who just like to soak up information. Welcome to our podcast where we discuss the latest and greatest in science. It's yours truly, Emma, the one who thinks that Gibbs shouldn't be free.
And August, the one who still doesn't know what fugacity is. With us today is truly a special guest, Hannah Fluidized Bed.
Hi there, guys. It's so nice to be here with you guys. I'm very happy that you wanted me here to talk about flow through packed beds. For me, it's truly a topic that everybody...
Oh my gosh, wow, same here. So Emma, before you say anything, I got some hot news for you. I was in LA with my friend Veronica last night, and I saw some sad little ginger talking about flows and packed beds, and I was like, no way, that's so niche.
I know, right?
Oh yes, I mighty do agree. Too many people are uninformed about...
Oh yes, I hate misinformation. So when I got back home, it was a must for me to do a little research.
Well, of course.
Well, as a fluidized bed myself, if you want, I could possibly explain the details.
Oh yes, details. I must tell you everything. So I found something that will change your life forever. Hear me out. Laminar flows through packed beds.
Wow. You have to let me know.
I know. So let me explain. Let's say we have a nice packed bed made of cylinders with a diameter and length of 0.2 meters. We also know that the packed beds have a density of 962 kilograms per meter cubed, and the density of cylinders are 1600 kilograms per meter cubed. What do you think the void fraction and the effective diameter of the particles are?
Well, let me think. Maybe you could do
Wrong. This is how you do it. We all know the void fraction is just void volume divided by total volume, but we could say it's also 1 minus the non-void volume divided by total volume. Since both volumes are within the same volume, this nice little fraction can be also expressed as the taken up density divided by the total density, aka the bed's density divided by the cylinder's density. Then all we gotta do is plug in our values to get 0.399.
Wow, Valley Girl podcast co-host, that's crazy.
I know, right? Okay, for the next part. So from what I've heard, effective diameter is just 6 divided by AV, where AV is the surface area divided by the volume of the particle. The surface area would be the area of the sides, plus the ends, which are 3 divided by 2 pi times the diameter squared. And the volume is pi divided by 4 times the diameter cubed. Therefore, AV is 6 divided by d, so the effective diameter is just d, which is 0.2 meters.
Why, yes, that is correct.
That is toast crazy. But what if it was, not laminar?
Emma, I need to hear on this. This might just change my life.
Alright, so from my friend Justin, I heard that for packed beds, you can find pressure differences for turbulent flows using this funky equation.
That is true, and what's really damn nifty about it is that it can be used for any flow, laminar, intermediate, and turbulent.
Ew, that equation is such an eyesore.
I know, right? But it gets even worse. If you want to make this equation dimensionless, it becomes this, which I guess is a little better.
I guess, but how do you find Reynolds number for packed beds? And that weird G symbol?
Well, I got you on this one. This weird G symbol is the mass flux, which is just mass flow rate divided by cross-sectional area. And Reynolds number can be solved using this equation.
Nice Hannah Fluidized Bed, but this equation is a little hard to work with.
Yeah, kind of like some people I know. Anyways, one of our viewers just sent us a problem to work out, so I'm going to give it a shot since it might be too much for you.
Rude.
Okay, so let's say air, which has a molecular weight of 28.97 grams per mole, flows into a packed bed of spheres with a temperature of 311 Kelvin, a pressure of 1.1 atmosphere, and a mass flow rate of 0.358 kilograms per second. The spheres have a diameter of 12.7 millimeters, and the bed has a void fraction of 0.38, a diameter of 0.61 meters, and a height of 2.44 meters. What's the pressure drop?
5.
Funny guess, but no. All we need to do is use that super long equation I was talking about. We're pretty much given everything except for the viscosity and the average density of the air. The viscosity, it's totes easy to find. We just need to look it up and is 1.9 times 10 to the 5th pascals per second. For the density, we can just assume that the air is an ideal gas, and we use PV equals nRT with some rearranging. We got density average is equal to the molecular weight times pressure average divided by R times temperature. Atmospheric pressure is nasty, so let's convert that to pascals, and let's plug everything in to get 1.221 kilogram per meter cubed. Now that we have everything, we can find the pressure drop, which is 4,970 pascals, not 5.
Very outstanding, Emma. You deserve a gold star. I really enjoyed that question. I'd love your use of...
Cool. So why spheres?
Excuse me?
Well, I don't know. Spheres are just weird.
I didn't make the problem.
Fine. So what if they aren't spheres?
I could just quit this podcast.
Wait. No, please. Please don't do that.
Okay, fine. I'll explain. A good friend of mine, Stan Friend, told me something a little while ago about spherosity shape factor, which is just a ratio of the surface area of the shape having the same volume as the particle to the actual area of the particle. So, since particles are pretty much spheres, the factor would just be 1 for spheres. For cubes, it's 0.81, cylinders, where dp equals h is 0.87, and the list continues. With these factors, we were able to calculate the effective diameter of particles and the mean diameter of the mixture of particles.
Let me guess, you have an equation for that?
Obvi, here they are.
Okay, not too bad. So do you have an example?
Oh, I think I have an example just related to this right here.
Let me see. Okay, not bad. So let's say this is a mixture of 3 particles, 25% with a diameter of 25 millimeters, 40% with a diameter of 50 millimeters, and 35% with a diameter of 75 millimeters. Oh, also curiosity is 0.68. What is the effective mean diameter of the mixture?
All you need to do is plug the values into the equation you were talking about, right?
Honestly, yeah, that's pretty much it. Here's what it looks like. And in the end, the mean diameter is 30 millimeters.
Oh, yay. That's so easy. Sadly, I think we're running out of time, but before I forget, do you know who Darcy is?
Duh, of course. Everyone knows Darcy.
Well, for laminar flow through a consolidated porous media, Darcy made a law used for calculating superficial velocity. Here it is.
Wow, what a nice petite equation. Do you have an example to go along with that?
Well, did you provide me one?
No.
Okay, well that's it for today. And this has been Science Girlies and our science podcast.
Oh, and Miss Fluidized Bed, you've been such an informative guest today. We're so happy you came here today.
Oh, wow, thank you very much.
Bye!
Hello there, class. My name is Dr. Hannah Fluidized Bed, and today we're going over Fluidized Beds 101. Now, who here has read the assigned textbooks that I assigned a couple weeks ago? Come on, guys. These 4 pages are important. What will you do when you go to work and don't know what the minimum velocity and porosity for fluidization is? Or what minimum fluidization even entails? Alrighty, I'll give you a quick summary for those of you who are behind so we can move on with the class period. Imagine you're flowing liquid up a tube with packed medium. What do you think happens when the velocity is too low? Yes, you.
Your media doesn't move?
Exactly. And if you increase that velocity when your pressure drop increases as well, eventually you come to a point where the gravitational force minus the buoyant force from your media equals your pressure force. From there, your media starts to move. This is called minimum fluidization, and the velocity and porosity that corresponds to this is minimum velocity and porosity. As you keep increasing the velocity from reaching minimum fluidization, your porosity will increase as well, but at this point, your pressure will decrease slightly and then remain constant. This is when you start to notice your media looks like it is boiling. If you keep increasing the velocity, then you will notice slugging. Now, if you take a look at the relationship I wrote up on the board, this is true because the volume of the media does not change as velocity changes. Now, when you have an irregular shape, this equation turns into this equation. Now, who wants to come up to the board and try out this here practice problem?
So, example 3.16 examines the minimum velocity for fluidization. So, we know that we have particles with a size of 0.12 millimeters, a shape factor of 0.88, and a density of 1,000 kilograms per meter cubed. And we know that these are to be fluidized using air at 2 atmospheres and 25 degrees Celsius. And we also know that the voidage at the minimum fluidizing conditions is 0.42. Now, part A asks us to find the minimum height of the fluidized bed if we know that the cross-section of the empty bed is 0.3 meters squared and the bed contains 300 kilograms of solid. So to solve this, we use the equation where it's L over L for the minimized fluidization is equal to 1 minus epsilon of the minimized fluidization divided by 1 minus epsilon. And plugging in our known values for that, we solve for the minimum height of the fluidized bed, and we find that there's 1.724 meters. Now, part B asks us to calculate the pressure drop at minimum fluidizing conditions. And for this, we use the equation delta P is equal to LMF times 1 minus epsilon times the density of air minus the density of the solid, all that times G. And plugging in our values, we find our answer, which is 9.78 kilopascals. Now, part C asks us to calculate the minimum velocity for fluidization. And so to do that, we use this very long equation, and it's 1.75 times the Reynolds number squared divided by 0.88 times 0.42 cubed, and those are that's phi and epsilon, and we add 150 times 1 minus 0.042 times the Reynolds number, and we divide that by phi squared and epsilon cubed, and we subtract the diameter cubed times these constants, and we set that equal to 0. And then we solve for the Reynolds number. And when we solve for the Reynolds number, we find that has a value of 0.07764. And we set that equal to the definition of the Reynolds number, which is d times v times rho divided by mu. And plugging in our known values and solving for v, we find the minimum fluidizing velocity is 0.00503 meters per second. Now for part D, we are supposed to repeat part C, but we have to pretend like we don't have the data for phi and epsilon. So in that, we would use the equation 3.138, and we would solve for the Reynolds number. And then using the same definition from part C, we would solve for v prime, and we would get 0.004618. So the part C and part D show that the velocities and the Reynolds numbers are similar, but the simplified equation would slightly overestimate both the Reynolds number and the velocity.
We finished that mini review. Let's talk about the expansion of fluidized beds. If the particles are small, aka have a low Reynolds number, the porosity or bed height will vary according to a proportionality constant and porosity, which depends on the particle size and shape, density, viscosity, and gravity. Constant for a particular system, that is. This applies to liquids with a maximum porosity of 0.8. When it comes to gases, there are too many factors that affect the system for this equation to hold. Now, if we compare this to a seesaw, you have your maximum. Oh god. The fluid has to be flowing fast enough to generate sufficient drag to overcome gravity and begin fluidization. That's your minimum, VMF. But not so fast that the solid particles fly away and don't behave as part of the fluidized system. How fast is too fast to maintain the properties of a fluidized bed? The terminal settling velocity for which particles are no longer accelerating creates the upper cap. Think back to settling in wastewater treatment. The range of velocities for very, very small particles can be expressed a ratio of 90:1. For very large particles, the range is smaller, more like 9:1. What does this mean? Large particles are more limited in their velocity when it comes to operating in a fluidized bed. Let's see how to find this maximum velocity in addition to finding the voidage of the bed.
Here are our given parameters. Using the ratio of 90 to 1 that I mentioned earlier, we can calculate the maximum allowable velocity, giving us 0.4526 meters per second. If you go above this velocity, then your particles will fly away. Now, if your operating velocity is 3 times the minimum velocity, you would get 0.01509, which would be below the maximum velocity. The way you calculate voidage, which describes how much free space is available for fluids to flow, is to find K1. You can do this by using this first equation with minimum velocity and porosity to calculate K1. Then, you can use this same equation, but using the operating velocity and K1 you calculated to find the voidage.
Honey, I finally taught my first class for fluidized beds. I'm so happy that I can finally make you proud. If you're listening, I hope that one day I get to see you and you get to see all the work that I'm doing here now.